The next chapter is syntax directed translation. Um, Last time we discussed about the syntax analysis, which is the second task performed by compilers. So after syntax analysis, semantic analysis is then performed. So in order to perform semantic analysis, the semantic analyzer needs some form of rules for the translation process. So as you can remember, the type of a rule which is required by, for example, the lexic analyzer, there should be a set of rules defined using most of the time using regular expressions. And for syntax analyzers, the rule which is required to direct or to govern the translation process or the compilation process is defined using the CFG, context-free grammar. Then for the semantic analyzer requires the rule which is added to the context-free grammar, because the context-free grammar is not directly used by the semantic analyzer. So the context-free grammar should be augmented with set of rules, and those rules are semantic rules. So the semantic analyzer requires a set of rules, the semantic rules, set of semantic rules that are associated with context-free grammar. So a context-free grammar that is attached with semantic analyzers, semantic rules. The semantic rules together we call that the resultant grammar as attributed grammar, as an attributed grammar, the attributed grammar. And this attributed grammar is the form of grammar that is used by semantic analyzers. So in order to associate the semantic rules to context-free grammar production rules, we do have two ways or two notations. So the first notation is named syntax directed definitions, and the second one is translation schemes. So the translation schemes and the syntax directed definitions are the two notations used to associate semantic rules to context-free grammars, so as to let the semantic analyzer perform the semantic analysis on the set of tokens. So after syntax analysis, then semantic analysis is then performed by semantic analyzer. So as we have discussed last time, the output of this one is parse tree, or syntax tree, whereas the output of this process, the semantic analysis, which is performed by semantic analyzer, is the annotated parse tree, annotated parse tree, or decorated parse tree. Why it is so called decorated parse tree or annotated parse tree? Annotated parse tree is that because at the end of semantic analysis, the semantic analyzer results a tree, a syntax tree, in which each attribute of the grammar symbol is computed. Its value is computed either from the child nodes or from the parent node. So that's why the resultant tree after semantic analysis is termed as annotated parse tree or decorated parse tree. So here we do have those two notations in order to associate the semantic rules to context-free grammar production rules, so that the semantic analyzer can use the a modified version of or an extended version of the context-free grammar. So once we attached the semantic all possible semantic rules to each production rules of the given CFG, then it becomes a suitable one to be used by semantic analyzer. So the syntax directed definition is the high level specification of translation rules, because it is hiding the implementation details. So that is the implementation. When we say implementation details, that is the order of evaluation of the semantic actions. And here we use this notation to associate production rules with set of semantic actions. And in translation schemes, we can just indicate the order of evaluation by using this notation. So what makes it different from syntax directed definition? So the semantic the syntax directed definition, we can just define it as a generalization of the CFG in which each grammar symbol has associated set of attributes, and those set of attributes can be inherited or synthesized attributes. So as you can remember, when we are defining a grammar, we just specify set of non-terminals and set of terminals. In general, in a given CFG, we do have the set of grammar symbols that are classified as non-terminals and terminals. So each grammar symbol in syntax directed definition, each grammar symbol is associated with set of attributes, and those set of attributes can be either synthesized attribute or inherited attribute. And what an attribute is here in the context of syntax directed definition, or in the context of grammars, when we are associating semantic rules with production rules. Attribute is nothing but, it can be anything That can be a string, a number, a data type, or memory location, or anything. So attribute is anything that may carry meaning, or that can provide meaning for the given production rule of CFG. So in order to just add the set of semantic rules to context-free grammar production rules, we need to associate or attach an attribute that can be either synthesized or inherited attribute to each grammar symbol, and that grammar symbol to which we can attach an attribute can be non-terminal or terminal symbol. So a synthesized attribute or the value here can be computed, or it is value, we can say the value of the synthesized attribute is computed from the values of attributes at the children of that node in the parse tree. So once we constructed a parse tree, we calculate the attribute values, values, that is the attribute of each grammar symbol in the parse tree, based on the type of attribute attached to the grammar symbol. So here a synthesized attribute is computed from the value of attributes at the children of that node in the parse tree, whereas the inherited attribute, as its name implies, inherited, that is the value of such attribute is computed from the parent and the siblings. So that's why it is named as inherited. So this inherited attribute is computed from the values of attributes are the siblings and the parents of that node in the parse tree. So the inherited attribute can be computed from the siblings, that is from the nodes at the same level, and that is from the same parent, from the siblings or the nodes from the same parent, and the parent itself, from the parent itself. So the attributes can be, as we already say, that attributes can be anything that may carry meaning. So the process of computing an attribute and its value is referred as binding, and that binding can be static binding or dynamic binding. When the calculation is performed prior to execution of the program, we call it static binding, and if it is computed or performed during the execution of the program, we call it dynamic binding. So let's consider those grammars, two grammars here. A grammar having those production rules: number drives number, digit or digit, and digit drives 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here what you are asked is parse this number 27. So just following the either top-down parsing approach or bottom-up parsing approach, and the derivation type, either rightmost or leftmost, you can derive the number 27. So using the given set of production rules, or using the given grammar, you can parse the number 27. Or you can also consider this the next grammar. You can also consider the next grammar, which is declaration, which is all about the declaration statement. Declaration, a rule for declaration statement. And the declaration statement, the rule for the declaration statement is stated as declaration drives type than var list, and type is driving, or type drives int or float, and var list drives id comma var list or id. So here what you can observe in this particular grammar is the terminal symbols are int, float, id, comma. Those are terminal symbols. And in the above grammar, the terminal symbols are the digits. The digits are terminal symbols. The digits from 0 to 9 are terminal symbols. So let you consider for the second grammar parts the input string or the declaration statement int x. So is it a correct? So when you are performing the syntax analysis, or when you are driving the given input string int x, that means you are performing syntax analysis, right? You are performing syntax analysis. So if you are able to drive this string int space x, then we can, in other words, we can say the statement, this declaration statement, is correct statement. If you are unable to drive this string, then we can say there is an error. There is an error in writing this declaration statement. So the derivation process of this string can be performed by simply using the production rules of the grammar, the CFG grammar. But here, what if you are asked to perform semantic analysis to the given string? So here, in order to perform semantic analysis, you need to associate semantic rules to each production rule of the given grammar. Consider the value, the attributes, like value for the first grammar 1, and for the second grammar, let you consider data type as an attribute, that can be associated to the grammar symbols, and define an attributed grammar by considering those two attribute types. For the first grammar, let you consider value, and for the second grammar, let you consider data type. So when we are associating semantic rules to production rules, we can have such general form. If we have a production rule defined as a drives alpha, and we want to associate semantic rule to this particular production rule, so we can associate semantic rule to this particular production rule by attaching possible attribute, synthesized or inactive attribute, to each grammar symbol used in this production rule a drives alpha. So the general form of the attribute specification can be represented as B drives F comma C1, I mean C1 F into C1 comma C2 comma up to Cn, where F is a function and B is either synthesized attribute or inherited attribute. So here, that means when we are attaching uh, an attribute to the grammar symbol, and here F is just a simply a function that calculates the value of the synthesized attribute or the inherited attribute. So in short, F is representing any function, any arbitrary function that is defined to compute the value of the attribute attached to a given grammar symbol. So if how we can attach a synthesized attribute, or how we can consider a given attribute as a synthesized attribute or inherited attribute. For a given grammar production rule, if attribute B is an attribute of A, an attribute of A, that is an attribute of non-terminal, which is on the left side of the production rule, an attribute that is attached to non-terminal on the left side of the production rule, and an attribute which is attribute of the grammar symbols in the production rule A drives alpha. So C1 here, and the C1, C2 and Cn up to Cn are attributes of the grammar in the production rule. We can say the grammar is, the attribute B is synthesized attribute here, because the calculation of this attribute B is from the attributes C1, C2, which are the attributes of the grammar symbols on the right hand side of the production rule. Here what you have to keep in your mind is any production rule which is represented as A drives alpha. Here we can consider A as parent when we are using the tree concept or the tree notation for representing production rules in the form of tree. We can say A is the parent and alpha part. The grammar symbols at the alpha part are considered as children of the grammar symbol A. So A and any non-terminal on the left side of a given production rule is termed as the parent of the grammar symbols on the right hand side of the production rule. So for example, if we have the production rule, let's say we have production rule A drives V, B and C. Another production rule B that drives B small a. So when we are representing this, we are representing those production rules as a tree, we can just draw like as A drives A, and under A we have terminal symbol V, non-terminal B, and terminal symbol C. Why we considered here V as terminal symbol, B as an internal, and C as terminal? That this V and C are terminal symbols because those grammar symbols do not have the production rule, and the grammar symbol B is an internal because it contains production rule which says B drives BA. So here for the first production rule, A drives BBC, we can put A at the top, and we can put below A the three grammar symbols. The grammar symbols. So from A we have a move, non-terminal. From non-terminal A again we have, and another we have here. So we can consider the production rule of the non-terminal A using the tree notation as A representing the parent node, B representing the right hand side of the non-terminal A production rule as the set of children, of non-terminal A. So here when we are representing, that means if we associate, when we are associating the attribute, we use dot notation or dot operator. So here if B is attached to the parent, and the B calculation or the value of B is computed from the attributes like C1, attribute of B which is C2 dot C2, and V attribute V is, let's say, C3. The attributes C1, C2, C3 are attributes of the grammar symbols in the production rule A drives alpha, and B is a synthesized attribute of A. Okay, so the attribute B is synthesized attribute of non-terminal A if the calculation of this non-terminal attribute is from the child. That is, when the semantic rule is defined for this particular grammar, we may define a the semantic rule like this. The attribute B is calculated from like V dot C1, let's say V dot C1 plus 3, we can say, or any semantic rule, any rule that may just provide meaning to the production rule can be associated. So the attribute is B. C3 is another attribute which is attached to terminal symbol V, and B is an attribute which is attached to non-terminal A. Since B, the value of attribute B is calculated from the child of the non-terminal A, which is an attribute from the attribute of V, we can say B is synthesized because its value is computed from the attribute at the children level. So from the children the attribute is calculated. So we used the child v and incremented the value of the attribute c3 by 1 and assigned this to attribute b.